My name's Art Annenberg, and this is my 1987 Ford F-150. This truck is factory equipped with a fuel-injected 4.9-liter inline-six engine that makes an earth-shattering 145 horsepower at 3,400 RPM and a peak torque of 265 foot-pounds at 2,000 RPM. This truck is also equipped with a 4-speed manual transmission. It's a Tremec T170 FT RTS TOD, and it's a B-code transmission according to the door tag, which means that the gear ratios are a 325 first, a 192 second, a 1/1/3, and a .783 fourth gear or overdrive. The rear differential is a Ford 8.8-inch rear with 355 gears. This truck rolls on 30-inch Falcon all-terrain tires. It is rear-wheel drive, and in its single-cab, long-bed chassis configuration, it has a wheelbase of 133 inches. Now, I drive this thing every day, so I know this truck is slow, and it's not good on gas. But I would really like to know, with a little bit of math and some MATLAB, how slow and bad on gas is it? And so begins my great quest. I started out by conducting a coast-down test on my truck. Using data from my high and low speed tests, I was able to back calculate the drag coefficient for my truck using a block pad sheet that I created. I ended up with a drag coefficient of 0.519. Once I had my drag coefficient value, I could start calculating the fuel efficiency of my truck using the backwards simulation model I made in Simulink. The way this simulation works is pretty simple. It starts out by pulling velocity over time data from a lookup table. In this case, we're using velocity over time data from the US06 drive cycle. This will simulate my truck driving along following this drive cycle. The simulation then takes this velocity data and calculates instantaneous road load power for my truck at any point in time. The road load power is essentially the amount of power required to move the truck down the road based on the aerodynamic drag, rolling resistance, acceleration force, and grade force that the truck is undergoing at different points of the drive cycle. After summing up the total road load power used, driving along the drive cycle for the entirety of the set range distance, the simulation then calculates your vehicle's fuel efficiency, CO2 emissions output, and total fuel consumption. I entered my drag coefficient, rolling resistance coefficient, frontal area and mass of my truck, and the thermodynamic, drive cycle, and drivetrain efficiencies into my backward sim and got a fuel efficiency of 13.85 miles per gallon and a CO2 emissions output of 642 grams per mile. That is pretty bad. However, this simulation's calculated fuel economy is actually pretty accurate. When this truck was new in 1987, it was quoted at a US EPA fuel economy of 15 miles per gallon city and 16 miles per gallon highway. So we're not really that far off. Now it's time to figure out just how slow my truck is. For this, we'll use a Ford simulation model that I made in Simulink. What this model essentially does is simulate a car launching from a dead stop and accelerating up to its top speed like you would in a drag race. We can use this model to accurately predict 0 to 60 and quarter-mile times and to produce road load force and performance envelope plots. This simulation even includes a transmission model to simulate shifting gears and a traction model to simulate the weight transfer of the car as it is launched. I used all the same vehicle data from my backward simulation, along with gear ratios, torque curve data points, and some chassis and drive wheel variables for my traction model. I ran the simulation code and got this from my results. My 0 to 60 time is 13.25 seconds, and my quarter-mile time is 18.98 seconds. Yeah, this thing is a dog. As you can see on the G's over mile per hour performance envelope plot, in orange is the ideal curve, and in blue is the actual curve with the shifting transmission model. You can see that I'm geared just below the traction limit. This is probably due to the larger 30-inch tires I have on the truck. And man, that 2 to 3 shift gap right at 50 miles per hour is absolutely killing my acceleration. Now, these simulation results are actually quite accurate. In 1987, this truck was quoted to have a 0 to 60 time of 12.8 seconds and a quarter-mile time of 18.9 seconds.
So we're pretty much spot on.
Now let's say that I am totally fed up with the bad gas miles that this truck gets, and I want to turn it into an electric vehicle.
Let's start here. This is a list of all the components I would remove from my truck if I were to convert it to electric, and the corresponding weight of each component. Once the engine and transmission, the associated accessories, and all their fluids are removed, along with the fuel tank and the 18 gallons of fuel, the total weight removed comes to 1,056.54 pounds. We'll subtract this from our vehicle weight and add on 200 kilograms for an electric motor. We can enter this new vehicle weight into our EV backwards simulation code. The EV backsim model is obviously different from its ICE counterpart. It includes the efficiencies for the electric motor and drivetrain and utilizes a regenerative braking cycle to increase efficiency. The EV backsim model must be iterated multiple times, and the pack weight must be added to the initial vehicle mass and run again until the pack weight finally converges. In the case of my truck, the pack weight finally converged at a weight of 1,637 kilograms for a total range of 350 miles. Now for fun, and for comparison, I also decided to make a series hybrid backsim model for my truck. Now this model is based off of the plain Jane regular ICE backsim model that I discussed earlier, with a few minor changes. The vehicle mass remains the same at 4,318 pounds. However, this model gets a regenerative braking cycle. I also bumped up the cycle efficiency to 100% because a series hybrid's engine will run at max BSFC all the time. My results for this backsim look something like this: a fuel efficiency of 14.7 miles per gallon, and a CO2 emission output of 604.7 grams per mile. Now let's compare the three versions of my truck: the original ICE powertrain, the hybrid powertrain, and the electric powertrain versions. In the weight class, the ICE and hybrid weights remain the same at 4,318 pounds. However, the electric version weighs a whopping 6,877 pounds. For fuel economy, the hybrid version of my truck only beats out the ICE version by a measly 0.85 miles per gallon. That's pretty disappointing. Obviously, the electric fuel economy is pretty hard to understand, but we can get a better grasp on that if we take a look at the fuel cost in dollars per mile. Now, for the hybrid and electric powertrains, our fuel cost kind of hovers around $2. Obviously, hybrid is just a little cheaper by a narrow margin, but our electric vehicle is dramatically cheaper by about half. This is a pretty dramatic improvement in fuel cost savings. Now let's take a look at CO2 output. The original ICE powertrain version of my truck puts out 642 grams of CO2 per mile. The hybrid powertrain is at 604 grams per mile, and the electric version is at 350 grams per mile. So, dramatic decrease in CO2 emissions from the EV. That's something to note. Now let's consider whether converting my truck to electric power is even financially responsible. Let's take a look at the fuel costs of my truck over a theoretical 250,000 mile lifetime. I would end up paying about $54,150. Now, if I were to convert my truck to electric power, I would pay $36,600 in electricity. However, in order to convert my truck to electric, I need to buy a battery pack, and at $125 per kilowatt hour for a lithium iron phosphate battery pack that has enough capacity for a range of 350 miles, I'd end up paying $30,700. This puts my total EV lifetime cost at $67,000. That's even more than the already egregious $54,000 that I would pay in fuel if I kept my powertrain stock. So to me, this swap is not worth it. But who cares? Let's take this EV thing a little further. These are torque and RPM data points for a 1 horsepower electric motor, and I'm going to use these data points for a Ford simulation for an EV version of my truck. All I need to do is add the data points to my code and scale the whole torque vector up. I'll bypass my shifting transmission model. Then I'll run the simulation and check to see if the quarter mile time matches the quarter mile time from the stock powertrain Ford simulation of my truck. I'll continue to scale the torque vector until they match. With my electric motor scaled to 175 horsepower, I got my quarter mile times to match. Now that I've sized my electric motor, I can turn my shifting transmission model back on. Now I'd like to use my Ford simulation to size a single-speed gearbox for my electric truck. I got rid of all the other gears in my transmission model except for one. I should note that I'm still using the final drive gearing from my differential as I haven't gotten rid of it. Then I'll set my single-speed gear ratio in the code and run the code, checking my quarter-mile time. I want to optimize my gear ratio for the minimum quarter-mile time. I continued to alter my single-speed gear ratio in step values of 0.5 to 1. Here is a plot of the quarter-mile times against the gear ratios I used. After performing this testing, I finally settled on a gear ratio of 5 to 1, which got the quarter-mile time down to about 19.56 seconds. If you take a look at the performance envelope curve in the top left corner, you'll notice that the actual performance envelope curve in blue is pretty closely spaced to the ideal performance envelope curve in orange. I would consider this exercise in gear sizing a success. This just about concludes the powertrain analysis on my 1987 Ford F-150. Thanks for watching. I hope you enjoyed.
Here comes the new shape of top, the big Ford pickup for '87 with a new aerodynamic